We here demonstrate our framework, DICE, short for Dynamic System Explanation, and in particular several tools: model simulation, interaction filtering, interaction classification, model extension, model checking, and sensitivity analysis. Here is an illustration of all components of DICE framework. We will demonstrate the functionality of those tools one by one with an easy graphical user interface or web-based interactive notebook.
In this demo, we will demonstrate the integration of different tools in our DICE framework with a very easy-to-use graphic user interface. And in this video, we will use a T-cell model as an example to show the functionality of our tools. So for now, you can see the whole user interface, which is also the GUI. And you can see there are several widgets with the sidebar on the left that let users to choose which tool they want to use in this GUI. Let's start with opening our model in the GUI. So basically, we can open one model or model folder. The model will be displayed in the spreadsheet format by clicking the File button in the Explorer. As you can see in the display model, each element has its regulators and other related information. And our model follows the bio-recipe format. The logic function with elements are defined with different notations in this format. The model will be checked with our predefined color names. So according to this check, the model will be classified in different levels for being compatible with other tools. And users can choose which model display options they want to see. The first column of element name is frozen, which allows you to scroll to the right, left to see, and you can easily edit the model in the GUI. We also provide a const on and off functionality for user to shut down an element or to activate one element. And these two columns are designed for maybe gene mutation or adding inhibitors. And we can do the simulation later to see the influence. The model can also be visualized as a graph, with green color arrows representing positive regulation and red color representing negative one. The graph is interactive, which means you can drag the nodes and rescale the graph. The relations between regulated elements and regulators are also synchronized in the GUI. Which is easy for a user to have clear insight of the model. Now if the model has initial values, you can use our simulator to simulate. We provide an editor for users to choose the simulation parameters, such as steps, runs, and simulation scheme. You can also choose multiple scenarios to simulate. Now in our examples, we are using the random scheme and set the steps to 500 and runs to 200. Yeah, we also want to simulate both scenarios. The simulation will take some time. The steps and runs are very big. And the results will be stored in trace text files. The viewer will show up to display the simulation results. Because we have two scenarios, we can visualize one element in these scenarios, or we can just visualize the results of one scenario. So let me choose two scenarios, and for the AKT elements, so for this plot, we can see AKT is increasing in scenario 1 while remain at 0 level in the other scenario. We can also analyze the results in just one scenario. If we are interested in the first 4 elements, we can plot the trajectories of these elements. And the heat map and each run can also be plotted if you want. The viewer is quite flexible. It allows you to store the simulation results in your computer, and we can import and visualize it later. So I'm going to show the simulation results of another GBM model built in our group. The GUI is very flexible and user-friendly, and users can resize and move the widgets. Dynamic tab in the GUI allows users to import different types of files, and when we need to compare different models or even reading output, we can open them together to see the difference.
Next up, we have a demo for Flute. Flute, or the Filter for Understanding True Events, is a tool that uses existing database resources on cell signaling events such as protein-protein interactions to provide a reliable metric for selecting high-confidence interactions from machine reading output. Flute integrates data from 5 different interaction databases: 3 protein-protein interaction databases, 1 protein-chemical interaction database, and a GoTerm protein interaction database. These different types of cell signaling events are represented in this sample input for Flute. In this file, we have a set of machine reading interactions, where every entity has a standard identifier, so it can be more easily mapped with the database resources that Flute contains. You'll notice that there are biological processes, proteins, chemicals, and more. To use the Flute database, we simply need a few input parameters. First, we assume the user has installed a local copy of the Flute database as specified in the documentation. We give the username, password, hostname, and the name of that Flute database. Here we're using the input file shown previously, and we've also specified an output folder. All we do is click Filter. Once Flute finishes, we have 2 different types of output files. The first output file is simply a list of all filtered interactions, so each interaction from the input that was found in at least one database in Flute. The second output file gives a bit more detail. For each of these filtered interactions, we have evidence types or scores from each of those databases in which the interaction was found. For example, for a GoTerm protein interaction, we have the evidence type, so how it was inferred and stored in the GoTerm database. For protein-protein interactions that were identified from string, we have a score for the experimental evidence, text mining evidence, or database evidence. For some of these interactions, they were found in 2 different types of databases. So, for example, in row 6, we have an interaction that was found in both string and in Reactome. Here we have a demo for the Violin tool. Violin, or Validating Interactions of Likely Importance to the Network, is a tool that can be used to judge literature-extracted events in comparison to an existing model. Each literature-extracted event, or LEE, is scored by Violin based on its similarity to a set of model interactions. Violin uses multiple scoring metrics to sort each LEE into one of 4 groups. Corroborations, extensions, contradictions, and flagged LEEs are all treated differently when looking at assembling or extending a model. Here we have our first input to Violin, our model file. Each row in this file is a model element. These elements have unique IDs, information such as cell line or cell type, location. Each model element has a unique variable and has rules for how it's regulated by other model elements. These regulations can be positive or negative. For violin, we also specify whether that regulation is direct or indirect. Here we show a sample input file to violin. This file contains a set of LEEs. An LEE is composed of two elements, both of which have been mapped to a unique identifier. One of these elements is upstream of the other. That upstream element or regulator may either inhibit or activate its downstream element. For each LEE, we also have a paper ID and evidence statement. Now we can use violin to score our set of LEEs in comparison to the model described previously. Depending on our purposes, we can choose to extend or corroborate. Here we'll select extend and classify. Violin returns the set of corroborations, contradictions, extensions, and flagged LEEs as described previously. If we want to extend our model, Violin has already determined which LEEs will be the most useful. It also provides a score, and a higher score is a better fit for extending your model. We can also use the Violin tool to visualize our classification results. In the top left, we see a distribution for the 4 categories of LEEs. We find that, by and large, extensions are most common in our input reading set.
In this section, I'm going to demonstrate the Clarinet module within DICE framework. Clarinet, short for Clarifying Networks, is a novel tool for rapid model assembling by automatically extends the dynamic network models with information published in the literature. Here, we provide an architecture of the Clarinet tool. On the left, you have the baseline model to extend and reading engine output that has a lot of events. An event collaboration graph ECLG is then created. In this graph, nodes and edges are assigned weight according to frequency class. Then community detection algorithm is applied to cluster the graph. While return passes, those clusters are further filtered and merged to help researchers find the best cluster to extend the baseline model. Let's get our tool set up. First, we need to know the baseline model and output from the reading machine. Here in cell 5, we highlight the necessary columns from the baseline model, which is compatible with the simulator in DICE framework. Also, in cell 6, we highlight the key information of each event we're going to look at. With those 2 inputs, we should be able to create an ECLG graph in cell 7. When we create our ECLG, some information is popped up, describing the number of unique paper IDs, average interactions per paper. To give you an overview, here in cell 8, we also show how the nodes in this graph look like. And we also show some characteristics of the graph, for example, the number of edges, number of nodes, and node degree histogram. Once the graph is created, we are going to process this graph and assign weights to the edges and nodes. First, in cell 11, we apply the function node weighting, during which each node in the graph is assigned a weight. Also, in this weight function, some less frequent nodes are removed from the graph to reduce the noise based on user inputs threshold, FCTH. Then we show some characteristic of the graph after removing those nodes and even draw a histogram comparison between before and after removing them. Then in cell 14, we assign weights to edges using either the FC method or the IF method. Up to now, both edges and nodes have weights that could be utilized to cluster the graph. Now, with the help of community detection algorithm, we cluster the graph. It says here we generate 6 clusters, or we call communities. For each community, the center of the community, the label, and the number of interactions within this community are listed. We can even visualize those clusters to give you a rough view how close they are from each other. Definitely, we want to save our work into some local directory and load it back. So we have a pickle function here as well. Of course, we have our baseline model that already contains some collections between nodes. We will use those existing collections to merge the cluster based on certain threshold. For example, if we choose the threshold to be 2, it turns out that cluster 1, 4, and 5 will be merged together. This big cluster will be one candidate cluster for the researchers to choose whether or not to be added to the baseline model. In this section, I'm going to demonstrate model checking module of DICE framework. Model checking can help modelers find whether a model can satisfy a certain property and return a satisfying probability. With its information, researchers can choose how to extend the baseline model. So first, let's set up the notebook and load the model spreadsheet. Given that we are using a statistical model checking tool based on Bayes' approach, we have to set several testing parameters, including testing mode, delta, coverage, alpha, and beta. Please refer to the following paper for detailed definitions. For default, we select testing mode to be best mode, delta to be 0.05, coverage to be 0.9, alpha and beta to be 1. Then it's ready for us to create a property against which we test the model. There are several ways you can create a property. You can either use the wrapper function we provide here, or you can write your own one manually following the rules. The property expression follows the syntax of BLTL, bounded linear temporal logic. For example, if you are going to create a property expressing your elements should reach value 1 and hold this value for at least one step within the future 50 steps, you should define your property expression like this. Then it's time to run model checking to find the estimation that the property is satisfied under the model we built. Usually, it takes time to run the model checker ranging from 1 to 5 minutes. Moreover, model checking also includes a subsection to determine how many simulation trajectories are required to obtain an estimate probability. The general idea is that the higher the coverage probability, the more runs it takes. Also, if you have a list of properties to verify, this small verification and visualization code can help you determine how many properties are considered satisfied given the threshold being 0.7. In this section, I'm going to demonstrate the sensitivity module of DICE framework. Sensitivity module in DICE framework aims to study how sensitive the elements in a network are to external and internal changes. Within sensitivity module, users will be able to find the most sensitive node and extract the most influential pathway. Let's get started. First, we have our notebook set up and be ready to note the model profile. In this cell 5, you are going to specify the model name. And for each model profile, you have to include the following columns: elements name, positive and negative regulators, levels that each element can take, and initial value that each element take at the first step. In DICE, we provide two modes of sensitivity analysis. The first mode is called uniform sensitivity analysis, when you want to calculate influence among elements only based on topology of the model network and function without dynamics. For this mode, sensitivity analysis can be conducted for both Boolean and discrete models. So in these cells, we run analysis and save the files into local directories. Here, I want to clarify some of the definitions. Sensitivity is the degree of elements being influenced by others. Impact is the degree of elements influencing others. Immediate refers to direct collected element pair, and remote refers to element without immediate collection. Then, we should be able to plot the immediate element sensitivity for all elements in a bar chart. Or we can plot the element influence matrix from any source to any target. This influence matrix can be calculated for immediate pairs and also for remote pairs. Moreover, we support the feature to inquire about the specific elements. For example, you are quite interested in an element. We can show the immediate impact from this element and the immediate sensitivity to these elements, or the remote impact from these elements and the remote sensitivity to these elements. Of course, we can show them either in a bar chart or a list of values. Furthermore, we should also return the remote influence from any chosen node A to any chosen node B. The other sensitivity mode is called scenario-dependent sensitivity analysis. This is when you want to calculate influence among elements based on the dynamics of the model, especially when you have different initial states. To start scenario-dependent sensitivity analysis, you first need to run a simulator to obtain trajectories of the model. You should refer to the simulator video for instructions and for setting the simulation parameters. It takes some time to get the simulation done, but after simulation, you should obtain trajectories of different scenarios stored separately and indexed. Then we run a similar analysis to get the rule files stored into local directories. All the functions for uniform analysis, including plotting bars, plotting matrix, inquiring about the specific elements, are all applicable to scenario-dependent analysis, which I won't show here one by one. But you have probably noticed the significant difference between uniform and scenario-dependent analysis results. With the sensitivity feature and some graph algorithms, DICE also provide another function called pathway analysis. This function returns the top pathway through which the source affects the target. For example, users can specify a source element, a target element, which will return the top pathway through which the source has most influence on this target. Users can even set to return the top n pathways, which are usually generated within seconds and can be stored into a data frame.